Hi, my name is Stan Forster. This is part 2 of our lecture on forces. In this part, we're going to cover Newton's 3 laws of motion. In the next part, part 3, we're going to talk about all kinds of forces that we can apply the 3 laws of motion to. Okay, these all tell us how we're going to combine forces. Okay, but these 3 laws of motion just tells us how to combine them. All right, but not specifically what kind of forces. It applies to all forces. Okay. So an object in a constant state of motion is going to remain in that motion unless acted upon by a net force. Okay, that constant state of motion could be at rest, or it could be some constant velocity along a constant speed along a straight line, constant velocity. Okay, and if an object is in constant velocity, then we know either at rest or at some constant velocity, then we know that the net force is 0. Now, the net force is the vector sum of all the forces acting on the object. All right. Mathematically, we're going to use this symbol sigma. Symbol sigma. It's a fancy, scary symbol, and it just means add them all up. Anytime you see that, it means add up all the stuff that follows. So there's a force symbol, a big F with an arrow over it, meaning this is a force vector. All right, and so that sigma means add up all of those forces. Okay, so we've already seen these. We've already seen these 2 forces acting in the same direction in part 1. We arbitrarily assign the 10 newtons to be positive, and the 4 newtons, well, then that has to be in the negative direction. So when we add them up, it's 10 plus a negative 4 equals 6. Okay, and so our net force, let's say this is a tension you're pulling off to the right, and there's a frictional force of 4 newtons off to the left. Okay, the net force, the one that's going to determine what the motion of the object is going to be the vector sum of those forces, or 6 newtons. Okay, we can also deal with forces that are not collinear. Okay, that are not in the same direction. Okay, so we have our 3 newtons and our 3 newtons, and we're going to call that upward or the y direction, and 4 newtons in the x direction, and those axes, that coordinate system is just completely arbitrary, but it's probably convenient. Okay, so how do we combine perpendicular components? Well, we use the Pythagorean theorem to find that magnitude. By the way, these bars around the A, I probably should have put an F in there, a big, but I wasn't really thinking about that when I did this. So put a big A in there, and these absolute magnitude symbols, that just means we're talking about the magnitude of this. So we're going to take the square root of the y component squared plus the square root of the x component squared. Why don't you work that out yourself? Okay, so 9 plus 16, and take the square root of that, and you're going to see that you end up with 5. Okay, what about the direction? This direction is 63.9 something, all right? And we round it off to 64. So that direction, theta, measured from the positive x-axis, is going to be inverse tangent of our y component, right here, divided by our x component. Now, I hope you did it before, but I'm going to read. This is important. So if you didn't do it before, do it now. Take the arctangent of 3/4. If you end up with something that doesn't round up to 64 degrees, you're in the wrong mode. You're going to need to figure out how to work your calculator. Okay, these are your tools. You need to know how your tools work. All right? If you end up with something that doesn't round up to 64 degrees, you're either in radian mode, degree mode, or something creative that your calculator manufacturer came up with. Okay, and you don't want that because it'll give you the wrong answer on the exam. Okay, let's talk about inertia. Inertia is the tendency in an object to remain in motion or at speed along a straight line. Okay, it's resistance to acceleration. Okay, we measure inertia in terms of mass or kilograms. Okay, so the more mass something has, the more resistance to acceleration it has. If you go up and you push against a Mack truck, do they even have Mack trucks anymore? Do they even manufacture those? Anyways, you push up against a big semi truck, you're not going to move it very much. Okay, it's got a lot of mass. It's got a lot of resistance to acceleration. Okay, if you take a child's tricycle and you push that, use that same force against a child's tricycle, you're probably going to put that in motion. That tricycle doesn't have as much mass. It doesn't have as much resistance to acceleration, and you're probably going to put it into motion. All right. Okay. Newton's first law. It's also called the law of inertia, and it's also kind of a sneaky way of defining an inertial reference frame. Okay, so this is kind of circular. Okay, an inertial reference frame is one in which Newton's law of inertia is valid. Okay, so that doesn't really tell you a lot. Okay, that doesn't tell you a lot until you think about it a little bit. Okay, where are they not valid? Okay, let's say you're in a rotating frame of reference. Okay, so you're measuring all your positions with respect to the inside of your car, and that car happens to be going around a curve. Okay, you feel, as you're going around that curve, you feel this force kind of forcing you out. That's actually your body trying to stay in motion in a reference frame defined by the road, okay, or the mountains and the earth and everything around you. Okay, you're going to try to continue on in a straight line, but your car is moving in a circle, and so it feels like you're being thrown out toward the side of the car. All right. It just means that the car is not a valid inertial reference frame. Okay, it's a rotating frame, okay, or accelerating as motion isn't changing. Okay, first law is a sneaky way of defining the inertial reference frame. All right. Newton's second law. Okay, what this one says is that the sum of all the forces is equal to the mass times the acceleration. You could have lots of forces acting on an object, but if it's going to remain one object, it's got one acceleration. All right, so you add up all the forces on the left-hand side, list out all the forces that could possibly act on this thing. All right, but on the right-hand side, it's going to be mass times acceleration. Okay, and this version over here, we've actually solved this for the acceleration. So if you need the acceleration, you sum the forces and divide by the mass. All right. Okay, it's also known as the law of acceleration. So what units are we going to use for this? Now remember, this is force times acceleration. Okay, so mass times acceleration. So mass is measured in kilograms. Acceleration is in meters per second squared. So we have kilogram meters per second squared. That's called a Newton. It's kind of appropriate, he comes up with Isaac Newton came up with the whole idea of forces. We might as well name it after him. When using Newton's laws of motion, you really, really, really want to be drawing a free body diagram. A free body diagram is a diagram that represents the object and the forces acting on it. All right, Newton's second law in the x and y direction. Okay, forces are going to have components. Okay, x, y, possibly even z. Right? So you can, we live in three-dimensional space. So the sum of all the forces in the y direction is going to equal to the mass times the acceleration in the y direction. Right? The same thing goes for the x direction. The sum of all the forces, components of the forces in the x direction, is going to sum up and equal to the mass times the acceleration in the x direction. Okay, those are all independent. All independently true. Okay, the third law of motion. Okay, forces come in pairs. They're equal in magnitude and opposite in direction. This is sometimes known as the action and reaction law. All right. So let's go ahead. Let's say example of action and reaction. You push on, let's say you grab a rope and you pull on your buddy. It's tied around your buddy's waist and you pull on him with 10 newtons, okay? That rope is pulling back on you with 10 newtons. There's a 10 newton force acting, you're exerting on your buddy, and there's a 10 newton force acting in the opposite direction, being exerted by that rope you're holding in your hands. Okay, so your action and reaction. So in part 3, we're going to go over an inventory of forces, all the different kinds of forces that can actually be applied using the 3 laws of motion. And we'll come back